by Shouvik Datta. And today's will be like an introduction zeroth lecture, which will be on 2D CFTs, and this will help for the upcoming lectures on quantum chaos also. So before we start, I would like to mention that today again at 4:30 p.m. we have another alternative career session discussion. It will be led by two other people like Napanita and Shudipto. So stick around for that also. Now over to you, Shouvik.
Okay, so thanks, Shubham, and thanks to the organizers for putting together this great meeting to share and learn. Okay, so today's lecture is going to be on 2D CFTs. So I'll provide an introduction to 2D CFTs, and as Shubham said, I mean, this will might help for next week's lectures on thermalization and quantum chaos. So this is a very wide field, as some of you know, so I'll just introduce some basic ideas and give you some examples and just as an entry to the subject, and then you can go and look up references and learn about this more. Okay, so I hope to cover, so first I'll begin with an example, which is the free massless boson. And then I'll talk about 2D CFTs in general. And I'll talk about the Hilbert space in 2D CFTs, the states and what operators you can have and how to calculate correlation functions. And if time permits, then I'll discuss conformal field theories on the torus, which is at finite temperature and finite size, so two periodic directions, which means you're on the torus. Okay, so that's the last thing. Okay, so let's begin. So I begin with the free boson. So, so consider the massless scalar field theory in two space-time dimensions. So this is the action. X denotes the scalar field, and these are your space-time coordinates. And yeah, here there is an overall factor. The overall factor is just a constant. I mean, it won't play a big role. The same action is actually also used for the bosonic string, but it's not going to play a role in this lecture. Okay, so this is a free theory with no interactions. It's too simple, but it does illustrate the essential features of a two-dimensional conformal field theory, as we will see. Okay, so first, notice that this action is Poincare invariant, and it's also invariant under scale transformation. So, for example, if you rescale your coordinates sigma alpha as lambda times sigma alpha, X is a scalar field, so it does not change under this coordinate transformation. And this derivative picks up a factor of 1 over lambda, okay, due to this. So there will be two factors of 1 over lambda from these two parts, and there will be an inverse factor of lambda squared from this measure. Okay, so that's going to cancel each other, and then you'll see that this action is actually scale invariant. That's the first thing. So another thing to notice is that if you have a mass term, then that's going to spoil the scale invariance. Okay, so if you have a term like m squared x squared, and you have the part in the measure, which is this. So this part is going to be invariant under the scale transformation. M is also invariant, whereas this is going to change under the scale transformation. So that's going to change. So adding a mass actually breaks scale invariance. Okay, so now let's look at the equations of motion. So we use light cone coordinates, which is time plus minus space, which is this. And the equation of motion is simply the Klein-Gordon equation, which is this. Okay. And a general solution to this equation, you can always write it as a sum of left moving and right moving parts, which means that they move along the light cone in this direction and in this direction. Okay, so that's this. Okay, so this was the equation of motion, and you could write down the general solution in this manner. And we can also take the sigma direction to be periodic, just to get rid of infrared divergences. We can keep it to be periodic. And then the general form of the equations of motion is going to be this. Okay, so the left moving part is, so this is a constant, and then this is a linear piece, which is, if you take these two derivatives, again, you get 0, and then this Fourier series, okay, over here. And similarly for the right moving part, you have got this. Now you can use this Fourier expansions, as you do in usual quantum field theory, to canonically quantize this theory. So the commutation relation between the field and its conjugate momentum, the scalar field and its conjugate momentum, is proportional to I, along with some delta function factors. And you can use these expansions over here, and you'll end up with these commutation relations between these alphas. Okay, so you can think of these as creation and annihilation operators, which obey this commutation relations. Okay, so we were on the cylinder. So sigma was a periodic direction, but we can do a coordinate transformation for now. We can go to the plane, and the manner in which this happens is that first you Wick rotate, and so you pick up, yeah, this is the location where my iPad does not work. So tau plus I sigma. Sigma plus I minus. Okay. So there's you Wick rotate, and then you take an exponential of that. Okay, which is this. And that takes you from the cylinder to the plane. So the tau going to minus infinity gets mapped to the origin of this plane, and where tau going to infinity actually gets mapped to infinity. Okay, so this is a complex plane plus infinity. Okay, so now let's look at the propagator. So so this is the action, but now we are on the z plane. And let's consider the path integral, which is given by this, and the 1-point function of the scalar field is simply given by this. Okay, so now we can perform the following manipulation. So we can take a derivative with respect to x of this combination. So this is a total derivative, and therefore it should be 0. And you can hit this on this and as well as this. So when you hit it on e to the minus s, you get this factor. After you have to like play around with some derivatives and then write and get this. And then when x hits this one, you get this delta function. This. Okay, so therefore you have this equation that this quantity over here should be 0, and that gives you this equation. This is the equation for the propagator. And throughout the lecture, I shall be using this notation that this delta is del z, and this bar of delta is del z bar. Okay, so this is the equation of the propagator. And notice that this is the analog of the Gauss's law for a point charge in 2 spatial dimensions. And the solution to that, I mean, the potential corresponding to that in 2 dimensions is given by the log. So you have noticed this log potential also in the matrix model lectures, and this is also something which appears over here. Okay, so this equation is essentially solved by the log, and up to some extra factors, the propagator is then given by the log of z minus w. Yeah, so please feel free to ask questions at any point. Okay, so we have this propagator, and this relation can actually be viewed as a consequence of the OPE, or the operator product expansion. Namely, if you take a scalar field close to another scalar field, it has got this logarithmic divergence, which is this, okay? And what this implies is that you can have this combination of x of w and x of z, along with a string of other operators, so O at y1, O at y2, so on. And if you take w close to z, the behavior of this correlation function is
Shouvik, can I answer your question?
Yeah, just 1 moment.
Yep.
Some regular terms. Regular is a regular in W minus C. Okay. Yes. Sorry, model. Yes.
Yeah. So I was just wondering, when you say can be viewed as a consequence of the operator product expansion, I was a bit confused about the phrasing.
Right. So the OPE is a more general statement. So over here, you can have some regular terms over here. So usually when you have an OPE, you can directly put angular brackets. You can take expectation values of the OPE. So you can think of an identity operator sitting over here. So that's equal to 1. And the whatever comes over here, all of them do not contribute. Okay, so the OPE is a more general statement than the 2-point correlation functions. That's what I mean.
Cool, thanks.
Okay, I hope that is clear. So we can separate this again, this OPE again, to left and right moving contributions, and then you can write this separately as the holomorphic contribution of the left moving part, and the right moving contribution, which is the right one, which is this. Okay, so we've looked at the 2-point function of the scalar operator itself in the 2D massless boson. And it's also easy to check that this theory has also got a conserved current, that this J mu is conserved. And the conserved currents are given by derivatives of the scalar field itself. Okay, derivatives with respect to Z and with respect to Z bar. And there are 2 conserved currents of this kind. And again, you can use the mode expansion or the Fourier expansion for the scalar field itself on the plane. And you can substitute this over here and here, and you can get that the conserved current itself has got a mode expansion or a Laurent expansion, which is this. Okay, similarly for the anti-holomorphic part. Okay, so we have seen that the propagator is given by this, or the 2-point function is given by this, and the currents are given by this. And you can use this information to find what is the 2-point function of the current. Okay, so that's a simple matter of taking derivatives. So over here in this equation, you can take 2 derivatives, one with respect to Z and one with respect to W. Okay, so similarly, you can take derivatives here. And upon taking 2 derivatives, it's very simple to see that the 2-point function of J's, again, J is defined in this way. So you take derivatives, and that's given by 1 over Z1 minus Z2. Okay, so that's the 2-point function of currents. And analogously for the right moving or the anti-holomorphic part, you also have got this. So now notice that these correlators have got a scaling behavior. Namely, if you scale Zi to lambda of Zi, so this is going to pick up an overall factor of 1 over lambda squared. Okay, so that's it scales in this particular way. And since we are in a free theory, we can find higher point functions of the current by using Wick contractions. Okay, so that was one conserved current, and we also have got more. So and there's also the stress tensor of this theory. You can take this action and you can find what the stress tensor is, and it takes this form. Once again, you can write this stress tensor components on the plane in Z and Z bar coordinates. And what you see is that the ZZ component is given by this. So this is nothing but the combination of the currents again. So this is something which is proportional to J squared. Okay, and similarly for the anti-holomorphic part, this is proportional to J bar squared. Okay, and the other component, the off-diagonal component, is actually 0. And an important property which the stress tensor has in a conformal field theory is that it is traceless. Okay, so it's the trace vanishes if you're on a flat surface. Okay, so we saw over here that the stress tensor is given by the quadratic combination of the currents, and this is a local operator. So this is a function of a single spacetime point. So, and we also saw that when we bring two scalar fields together close to each other, there are divergences. So when two operators collide, there are OPE singularities. So in order to define composite operators of this kind, which is over here, the stress tensor is a quadratic combination of the currents, we have to subtract out this OPE divergences. And this is something which is called normal ordering. So the way it works is as follows. So you take your currents. So this del X is J and another del X is another current. And you subtract out the divergent part. Okay, so this was the 2-point function of sorry. So this was the 2-point function of JZ JW. Okay, and this was we saw that this is equal to 1 minus Z minus 2 squared. Okay, and so the idea is to subtract out the OPE divergences while defining composite operators. Okay, so you can use again the mode expansion for the scalar field, and you can subtract out this divergence, and you can write the stress tensor in terms of the modes again. And what you'll see that the stress tensor again itself has got a mode expansion, where these LMs over here are defined in terms of the modes of the scalar field itself in this manner. Okay, so this LM and L0, they are defined in this way, and in fact, you can extract out a single mode of the stress tensor by performing this contour integral. And yeah, from this operator, you can get the modes. Okay, so I hope this is clear. So the stress tensor has got this mode expansion, and we saw that the modes are given in terms of the modes of the scalar field in this manner. And we also learned that the modes of the scalar field, they obey this commutation relation, which came from the commutation relation from the usual canonical quantization, and it obeys this commutation relation. Now you can check as an exercise that if you use these expressions for the stress tensor modes, and if you use this commutation relation between the alphas, you arrive at this algebra. Okay, so you arrive at this Virasoro algebra with the central charge C equal to 1. So I'll come to what the central charge is, but you get this form of the Virasoro algebra. Okay, there might be some regularizations which you need to do in order to arrive at this central term. Okay, so so this is the Virasoro algebra. So there is one for the left moving part, and there is another for the right moving part. And as I mentioned, C over here is the central charge of the theory, and it is a measure of the number of degrees of freedom of your system. Okay, and for instance, the fact that it is a measure of the number of degrees of freedom, it can be seen in the high energy density of states. So this is actually a universal result that at asymptotically high energies, the density of states in a conformal two-dimensional conformal field theory grows in this manner. Okay, and it is proportional to the central charge. So the exponent is actually proportional to the central charge. So if the central charge is larger, you have more states at high energies. Similarly, there were lectures on entanglement entropy, and one can actually find what the entanglement entropy of the ground state is in a conformal field theory. And it again takes a universal form. So if you have a line, an infinite line, and if you look at the entanglement entropy of a subsystem of a finite region of length L, it takes this form over here as log L. And the central charge appears again over here. So this is another way to see that this measures the number of degrees of freedom, as entanglement entropy is a measure for measuring how quantum information is distributed across your system. And the central charge also appears over here. Okay, so now let's look at this algebra a bit more carefully. Let's ignore the central term for a moment. And let's look at the rest of it. So that's given by this and this. So this is something which is called the width algebra. And you can see that you can realize this algebra by using this differential operators. So you can take this combination of these differential operators and act it on any function, and you can see that it obeys this commutation relation. Okay, and once you exponentiate this, okay, so before that, and these actually correspond to infinitesimal transformations of the form. So if z goes to epsilon n of z, where epsilon n of z is given by this. Okay, and you can exponentiate these generators, and it gives nothing but a Taylor expansion. So the finite versions of these infinitesimal transformations are z going to another function and z bar going to the same function with z replaced by z bar. Okay, so what this implies is that the conformal transformations in 2 dimensions are analytic functions which take you from functions from z to functions of z. Now we can look at the algebra of the modes 0 plus 1 and minus 1. And that's again given by this, but the modes take these values. Once again, these can be realized using these differential operators, which is this. And these two commutation relations, the generators of these generate the group SL2R on the left and SL2R on the right, which is SO2, 2. And this is the global conformal group in 2 dimensions. And it can be seen that the translations corresponds to these modes. So if you take minus 1 over here, you just get del z and del z bar, which corresponds to translations. Similarly, rotations corresponds to this combination. You can go to polar coordinates, and you can use these forms of these derivatives, and this takes this form. This is yeah, just like angular momentum. And similarly, scale transformations correspond to this combination. And once again, in polar coordinates, this takes this form. But the fact that this is scale transformations, you can see that this, if you act it on this, it's going to give you minus delta. So R to the delta is sort of an eigenfunction of this operator, and with the eigenvalue delta. That's scale transformations. And you also have special conformal transformations, which are given by these generators. So these correspond to an inversion followed by a translation followed by an inversion again. Okay, and the final.
Maybe 1 second. Like
yes.
The room is very quiet. Like so.
Maybe I'm going too fast.
Maybe we can ask some, like, I mean, if.
Or maybe this is all known.
Yeah, either that this is all known, or like we are.
Going yeah. Maybe we can ask a bit whether this is all known.
Like,
or I'm going too fast. Yeah,
either very bad or very good, which is quite rare in a seminar. Like,
well, so those of you who think I'm just saying known stuff, could you please raise your hand so that I can just get an idea of the percentage of.
Oh.
Looks close to 40% or something. Combine. Yeah, so it's around like 1/4. Yeah. Okay.
So maybe from the from the rest of the people, like maybe if there are some questions, since
Yeah,
we're like half an hour in, maybe we can pause for like
I mean, if
2
you guys
minutes.
have any questions, please do
Yeah.
ask.
Okay, thanks for the feedback. Yeah, so I can go at this pace, right? Is it okay? Or what do you think, Shubham? Should
I mean, for me it's fine, but like I don't know, like maybe we can ask people like if this pace is fine, like by giving a thumbs up, maybe.
Yeah.
I mean, if you think, guys, yeah.
Do we not have access to those advanced zoom features that they used in strings? Like, you can take a poll, that kind of stuff.
I don't know.
Okay, so not everyone thinks this pace is fine. I mean, I don't know. Should I go faster or slower? But anyway, let me continue.
Let's continue with this case. I mean, if people need you to slow down, maybe they can ask questions.
Yeah.
Let's slow you down.
So there is a suggestion from Avinash Swain. I think this space is fine. I personally would rather prefer to spend some more time on torus that's comparatively new.
Okay. Okay, so let's keep going. Okay. Okay, so we saw that these are the generators for the global conformal group, and the global conformal group is SL2R times SL2R. And the finite versions of this is that is Z going to this fraction and Z bar going to this fraction. So the full conformal group is like Z going to any function of Z, whereas the global part is this. Okay, and these actually correspond to scale transformations, rotations, and special conformal transformations. You can see through these pictures that you can start with some grid over here, you rotate it and scale it to a smaller version of it, and you can also twist it in this way. But the important point is that the local angles remain conserved under conformal transformations. Okay, so we can work out the OPE of stress tensors of the free boson, once again, by using Wick contractions. And the result which you get is this. So if you have got two stress tensors and the OPE of that has got a central term, which is this, and two other terms that is proportional to the stress tensor itself and the derivative of the stress tensor. And once again, we are doing it for the free boson theory, for which the central charge is 1. And related to the question which Madhu asked earlier, so the OPE is a slightly more general statement than correlation functions. So you can take this OPE and take the expectation value in the vacuum state. So, so you take the expectation value, so there's the central term over here, and expectation values over here and here. Okay. So we are doing this on the plane. So the expectation value of the stress tensor on the plane, just by translation invariance, is 0. And this is just the derivative of this object. This is just the derivative of this object. So this is also 0. And therefore, the 2-point function is simply given by this, which is just this leading term. Okay, so we have seen the stress tensor and the current in the free boson theory, but how do these transform under conformal transformations? So, so this is the current given by the derivative of the scalar field, which is this. And if Z goes to f of Z, this is the conformal transformation, you can simply use the chain rule, since this J is defined in this way, you can simply use the chain rule to see that the current transforms in this particular way. Okay, so that's a simple relation for the transformation rule of the current. Okay, hopefully this is going to be something new. Let's see. So let's look at how the stress tensor transforms. Okay. So the stress tensor, as we saw, is that it is given by the normal ordered combination of two currents, which is del x. And since this is a composite operator, we have to like point split them. Okay, so over here we check z plus delta plus half and z minus delta plus half. Okay, and we subtract out the OP divergence, which is coming from the 2-point function of currents. Okay, so similarly, you can so T of z is defined in this way. So T of f of z is also defined in the same way. So you have this combination of the currents over here, and you subtract out the OP divergence, which is this. Okay? And finally, you take the delta going to 0 limit.
So Shouvik, in writing down the OP divergence, you just use the expression for the 2-point function of currents, right?
That's right. Yes, that's what I. Yeah. Okay. So T of z is defined in this way, and T of f of z, just by following this, is following this thing above is given by this. All right. So so we are interested in finding how the stress tensor transforms. So one can once again use the chain rule. So let's start with this. Let's change variables from z to f of z. So you pick up these extra Jacobian factors, and you have this. So this del x, which is a function, which is now a function of f of z, and del x, which is a function of c, which is this. Now notice that this combination is precisely this combination that appears in T of f of c over here. Okay, so we can write this shaded part using T of f of z plus this quantity. All right, so that's what we do. So in the next step, we write this part as T of f of z plus this part. That's what we have. Okay, now you need to take the delta going to 0 limit. All right, and yeah, so you just need to Taylor expand this ugly expression, I mean, which you can do in Mathematica, for example, and just look at the finite part. Okay, because the divergence is subtracted out. And once you do that, you get this part, just like the current, the stress tensor now transforms with 2 powers of del f, del z. And you have this additional piece, okay, which is the Schwarzian derivative, which you have met earlier. So this is one way to arrive at the Schwarzian derivative. I mean, this is, I think I've seen only this derivation. So in most of the cases, people write the infinitesimal version of the Schwarzian derivative, and then just show you that this is the Schwarzian derivative, and whose infinitesimal version is this. But at least for the free boson theory, there's a very explicit way to arrive at what the Schwarzian derivative is. And this is used over and over again in various places. And one thing to notice is that if you look at the global conformal transformations, which is z goes to z plus b divided by c plus d. This part actually vanishes under these transformations. Okay, so the summary so far is that we looked at the free boson theory, and we saw that it has got a conserved current, and it transforms in this manner. And this is an example of a primary operator. Okay, so this actually one can write this to the power 1. So this is a conformal primary of weight 1. And the stress tensor also transforms.
Hi, Budhaditya has a question.
Yes, please.
Yeah, hi. I didn't get your last point very correctly. So the Schwarzian derivative vanishes for any conformal transformation?
No, only under the global part. Yeah. So if z goes to az plus b divided by cz plus d.
So for any choice of a, b, c, d. As long as or the AD minus BC is one.
SL2R, yeah, so it has
Yeah.
to obey the determinant condition. That
Okay.
minus BC is equal to.
Thank you.
Okay, so we saw that there is a conserved current and it transforms in this way. And this is actually an example of a primary operator. So this transforms with weight 1. And the stress tensor also transforms in a similar way, but there is this extra term which we saw. This is a Schwarzian derivative term, but this is called a quasi-primary operator because there is this additional piece. And it's got the holomorphic weight or the conformal weight to be 2. Okay. And we also saw that one can find correlation functions on the plane, and the 2-point function of the stress tensor and the current is given in this way. All right. And finally, we saw that the stress tensor has got this OPE, and an equivalent statement into the CFT is that of the Virasoro algebra. One can actually arrive at the Virasoro algebra from the OPE, and it takes this form. Okay, so we worked out things for the C is equal to 1 free boson theory, but these relations continue to hold more generally into the CFTs. Okay, so I come to an end of this part. So if there are any questions or comments or anything else anyone needs to add, yeah, please.
Yeah, so Shouvik, I wanted to ask, like, so you called the current a primary operator, and then you called the stress tensor a quasi-primary. So I'm just trying to understand what the distinction is and why the terminology.
Yes, so yes, so note that under global conformal transformations, which is again z goes to z goes to az plus b divided by cz plus d. Okay, this part, the Schwarzian derivative actually vanishes. Okay,
Right.
and for that, the current as well as the stress tensor transform in the same way. So you just need to keep track of this term.
Right.
Okay. So so if you consider the global conformal group, so this is a primary. I mean, the current is this is a primary as well as this is also a primary. But only if you consider go beyond the global group. If you consider the full Virasoro algebra, then this part becomes important, and the stress tensor is loses its character of being a primary anymore. And that's why it is called a quasi-primary.
Okay, so would it be correct to say that JZ and TZ are the current and the stress tensor are both quasi-primary operators, but only the current is a primary operator? Is that correct?
That is correct. That is correct. So yeah. So more generally, all quasi-primaries are sorry. All primaries are quasi-primaries, but not all quasi-primaries are primaries. Yes.
Cool. Okay. Thanks.
Okay. Any other questions? Okay. Hopefully now we'll have less math and slightly more entertainment. Let's see.
There is a question in the chat. What is the significance of the term primary?
We'll see. We'll see. That's a good question. Yeah, we'll see. Okay, so we went through some amount of math. So it's now time for some stories. So, so when a system undergoes a second order phase transition, its correlation length diverges. And at this critical point where the phase transition happens, there is an emergent scale invariance. And in 2 dimensions, one can show that scale invariance is equal to conformal invariance. at least for unitary theories, one can show this, and this was shown by Polchinski. So the way this is shown, since I have time, I can say a little bit, is that one can look at the 2-point function of the trace of the stress tensor. And one can show just by using scale invariance that this is 0. Okay. Now you can use reflection positivity in unitary theory. So if the 2-point function is 0, then this operator itself is equal to 0. So scale invariance implies conformal invariance in 2 dimensions. However, in higher dimensions, this is not true.
I have a question.
Yeah.
What is reflection positivity?
Reflection positivity is that if you have like the quadratic combination of operators, that's going to be positive. Okay, that's greater than or equal to 0. Yeah. And if this is equal to 0, I mean, if the 2-point function itself is equal to 0, then that implies that the operator itself is null. I mean, it's 0.
I see. Okay.
Okay. So let's look at a system near the critical point. So this is a Monte Carlo simulation of the Ising model. Right at the critical point, little below the critical point, and slightly above the critical point. And so black represents upspin and white represents downspin. And what we're going to do is to look at a specific system size, and then we're going to look at larger system sizes and look at the long distance behavior. Okay, so first, let's look at the system below the critical point. As you zoom further and further out, as you look into the long distance behavior, it goes to this ordered phase over here. Okay, so it's like a ferromagnet. And right above the critical point, as you zoom further and further out, this is what happens. We get a disordered phase, which is that of a paramagnet. And very interestingly, at the critical point, as you zoom further and further out, it looks more or less the same across all scales. Okay, so you really cannot distinguish between the scales of your system. So this is scale invariance. And what this implies is that measurements at any scale at the critical point yields the same results. Okay, and so this is why conformal field theory is useful for describing systems near the phase transition or at the phase transition.
Scale invariance and conformal invariance are same in higher dimensions also, or
no, it's not the same. Yeah, it does not imply scale invariance does not imply conformal invariance in higher dimensions. Actually, an example in three dimensions, 3 space-time dimensions, is Maxwell theory. It is scale invariant, but it's not conformal. Yeah. Doesn't so it's not invariant.
Can you please repeat your last line? So, I'm sorry, I actually missed that.
Yes. So I was saying that for 3D Maxwell theory, it is an example of a theory which is invariant on this, which has got scale invariance, but it's not conformal invariant. Yeah, so it's not invariant under special conformal transformations, but it's invariant under dilatations.
Okay, actually, I'm talking about your previous slide.
Okay.
Yeah.
Yes, so as you can see that at the critical point, I mean, across all length scales, the system remains, I mean, you cannot really distinguish across length scales, okay, at the critical point. So what this implies is that, I mean, if you measure correlation functions, okay, at the critical point, you're always going to get the same result. That's what I was trying to say.
Yeah. Okay, thanks.
Okay. Okay, so by now CFTs have got several uses. Namely, they form landmarks in the space of quantum field theories, in the sense that you can think of the space of quantum field theories as CFTs plus their deformations. Okay, and you can and the universal feature is that at the long distance, or the IR behavior, is usually described by a conformal field theory. Right? So usually theories flow to an IR fixed point, which is described by a CFT, and at the ultraviolet as well. I mean, one can find fixed points which are described by CFTs. And there are also theorems such as the C theorem. One can find C functions. Yeah, let me just say this and then I'll take the question. One can find C functions which monotonically decrease along the RG flow from the UV to the IR. And the C function at these fixed points take the values of the central charge of the CFT description in the UV and the CFT description in the IR. So what this means physically is that that in the UV, the description of the system involves a greater number of degrees of freedom, and as you integrate out and move to the IR, you lose this information, and thereby your central charge decreases. Yes, there's a question.
Yeah, so going back to the I just wanted to you had given an argument like invoking reflection positivity and the 2-point function for the trace of the stress tensor being 0. So in higher dimensions, what is the like what goes wrong in this argument?
Yeah, that's a good question. Yeah, right now I don't know. Yeah, right now I don't have an answer. Yeah, but I can look up and tell you. Yeah.
Okay, yeah.
Sorry, yeah. So actually, there's a review by Nakayama that discusses scale versus conformal invariance at length, I mean, across dimensions. Yeah.
Okay.
Yeah, but I don't have an answer right now.
Yeah, it's okay.
Okay, and all of us know that this is general knowledge that CFTs play a major role in understanding gravity in ADS, and this is the famous ADS CFT correspondence. And this gives a non-perturbative framework for calculating the quantum gravity path integral. Okay, so now, yes. Yes, Pratik, you can ask your question.
Pratik, are you there? You have raised
Hi.
your hand.
Yes. Yeah. So the monotonicity of C function is obvious, or is lies in the some statements about some theorems or something?
Yeah, so it's not obvious. I mean, one has to derive it, and the way it is derived is by looking at the 2-point function of the stress tensor again. Yeah, one has to look at various combinations of components of the stress tensor and see how that changes under the RG flow, and then it's derived from there.
I see. So you, when you integrate out the, I mean, when you do the integrate out thing, so it always means that it should decrease, right? So there should be.
That's an intuitive way to understand it. Yes. Yeah, that's an intuitive way to understand it.
Yeah. Okay. Thank you.
Okay, so now let's discuss the Hilbert space of the CFT and operators and correlation functions of these operators. So we saw that for the free boson theory, it had a conserved current which transforms in this way under conformal transformations, and this is an example of a primary operator. And more generally, you can have primary operators that transform under conformal transformations with some holomorphic part, which is this, and some anti-holomorphic part, which is this, and this H and H bar over here are the left and right conformal dimensions of this operator, or the holomorphic or the anti-holomorphic conformal dimensions of this operator. And in the context of statistical physics, while describing phase transitions and so on, these numbers h and h bar, these correspond to the critical exponents. Okay, so since we have a large symmetry algebra, we can classify the states in a CFT using these symmetries. Okay, so the states in a states in CFTs can be organized into highest weight states of this Virasoro algebra. So these are called the primaries. So this is actually the reason why they are called primaries. This is important. You can always decompose the Hilbert space of your theory of a CFT into primaries, which are this highest weight states, and excitations on top of them. Okay, these are excitations built on top of these primaries. Okay, so so the Hilbert space of your theory is and decomposes itself into these sets of states. Each of them are called Verma modules, and all of them like originate from a primary operator. I think this is the reason why they're called a primary. Okay, now I'm saying a primary operator and primary state synonymously because there is a state operator correspondence by which you can act this operator O on the origin, on the vacuum, and thereby create an excited state corresponding to that primary operator, and which is denoted by HP over here. Okay. Now, what are these descendant states? So you start with some primary state, you act it by a bunch of Virasoro generators with these negative modes, and thereby you can get these descendant states. Okay. So let's see this in detail. So a generic state in a 2D CFT, you can write it in this way. So this has got 3 labels. So the first label is the that of the primary operator, where it comes from. So that's the primary. And then it's the descendant level. So which level it is. So what is the additional energy by which you have excited the state? And so this is the descendant level. And there is another label, which corresponds to the integer partitions of this descendant level. Okay, so at level 0, you have this ancestor or this primary state, which is this. Okay, so that's this. So at level 1, you can, which is this state over here, you can act by L-1 on HP. And get this state at level 1, and this has got energy HP, and this has got energy HP plus 1. Okay, and similarly at level 2, you can do it in 2 ways. You can increase the energy to HP plus 2 in 2 ways. You can do it in this way. You can act 2 L1 generators on the primary state and get this. What you can also do is to act by L-2 on HP. Okay, so that and thereby you can raise the energy by 2 units. So at level 2, you can do it in 2 ways. And then at level 3, which is this over here, you can do it in 3 ways. So you can do L-1 cubed HP. You can do L-2, L-1 HP, and then L-3 HP. Okay, that's what you can do. Yes, Shubham, just a moment. Yes, and then at higher levels, so these, there are 3 because there are 3 integer partitions of 3. And at next level, you've got 5 states because there are 5 integer partitions of 4. And then you've got 7 states because there are 7 integer partitions of 5. And then 11 states because there are 11 integer partitions of 6 and so on. Yes.
Is it always guaranteed that at a certain level these states will be linearly independent? You will get
yes, so yeah, so that's a good question. So these states are actually not linearly independent. It's very bad. I mean, these are not orthogonal. In fact, if you take inner products of say, for example, this and this, it is non-zero. Okay, so it's not orthogonal. So yeah, you can always go to an orthogonal basis and work with that. But, and yeah, and such a description exists. It's which is called the oscillator basis for the Virasoro algebra. And if you work with that basis, then the states at each level are going to be orthogonal and independent. But the usual Virasoro basis, which is this, it's not orthogonal. Yeah.
Orthogonality is perhaps fine. I'm saying linear independence. Like, I mean,
no,
only
it's not.
I mean, linear independence and orthogonal. I mean, if only it's linearly independent, then only you can think about Gram-Schmidt orthogonalization, right? I mean, I'm just asking.
Yes, like, yes. Sorry, I misspoke. Yeah. It is linearly independent. Yes. Obviously, the number of states at each level, number of independent states, linearly independent states at each level are given by these numbers. Yes.
Okay.
That is correct. Yes. Sorry, I misspoke. Yeah, but they are not orthogonal.
Yeah. Okay.
So Shouvik, I'm a bit confused. I thought that for generic values of the central charge, they are linearly independent, but you can have linear dependence, right? For like you can have null states for specific.
Yes, that's why you have got this asterisk over here, which says that it applies to CFTs with directional symmetry. So this, so which shows that you are an expert. And so for special values of the central charge, one can get additional null states, as Madhu was saying. So the way that happens is that you can look at the inner product of this state with itself, okay? And for some specific values of the central charge and HP, such norms can actually vanish, okay? And these things happen in rational CFTs. Yeah, so I'll come to what is a rational CFT and what is a irrational CFT in a few slides, but let's stick to irrational CFTs for the time being, for which the description is simple.
There is a question in the chat. So,
yeah,
what is irrational CFT?
Yeah, I'll come to that. Yeah, I'll come to that in a few slides. Okay, any other question? Okay, so we saw that at each of these levels, we have these degeneracies, and one can actually write down a counting function. Yeah, please.
So the orthogonalization in the say for irrational CFT, the orthogonalization at the level, is that independent of HP?
Yeah, HP is just a parameter. I mean, that's somehow. I mean, the orthogonal basis which I'm aware of, is probably the only one which exists. That actually involves HP as a parameter. What do you mean independent of HP? I mean, writing the basis
as in at a particular level are the independent. Are the partition number worth of independent states?
Yes.
Like is the linear combination independent of HP? Yeah.
Yes. You mean the coefficients in the linear combination, do they depend on HP or not?
Yeah. That's what I mean.
Yeah. I mean, if you can always go to an orthogonal basis. Oh, okay. So if you try to write these Virasoro generators in terms of an orthogonal basis, then the coefficients of that can depend on HP. Yes, I mean, that is possible. Yeah. Yes, there is another question.
Okay, thanks.
Yes, so can you just, for the examples that you have given in this slide, can you explain what for these examples this partitions of the integer m means? That is the
yeah. Thanks for the question. Yeah, so you can look at, so let's look at integers. So you can, one, you can always write it as one. Okay, so that's only one single integer partition. So 2, you can write it as 2. You can also write it as 1 plus 1. So there are 2 possible ways of doing this. Then again, 3, you can write it as 3, and then 2 plus 1, and then 1 plus 1 plus 1. Okay, so notice that these 3 corresponds to these 3 over here, these 3 descendants. Okay, so 3, the number of integer partitions of 3 are these. Okay, so so you can write Pn. So this is the number of partitions of an integer n. So this says that P of 1 is 1, P of 2 is 2, and P of 3 is 3. Now you might guess P of 4 is 4, but it's not. So actually P of 4 is actually 5. So 4, you can write it as 4. You can write it as 3 plus 1. You can write it as 2 plus 2. You can write it as 2 plus 1 plus 1. You can write it as 1 plus 1 plus 1 plus 1. Okay, 1, 2, 3, 4, 5. So you can write it in 5 possible ways. Okay, and that's why you've got 5 over here. All right. And similarly, 6, I mean 5, you can write it in 7 ways. And then, yeah, so on and so forth.
Yeah, but in that way, P of 0, shouldn't it also be 1?
Yes, P of 0
there...
is 1. Yes, yes, that is correct. And P, and that corresponds, oops, sorry. Yeah, yeah. Can you see my screen?
We just for a few seconds it was there. Now it's again gone.
Okay. What is it? Oh yeah. Yeah. Yes. Sorry, my writing is all gone. But yes, indeed, P of 0 is 1, and that actually corresponds to this, which is the primary.
Yeah. I was confused because in that case, in the second bracketed thing, you have written 0, right?
Yeah. Well, that is. Well, I mean.
So
well,
I was wondering what.
Very seriously. I mean, this is special. I mean, this is special. I mean, the P of n, I mean, starts from the descendant. This is not really a descendant. So yeah.
Okay.
Yeah. Okay. Yeah. Sorry if that caused any confusion.
I had a related question. So for this level 2 descendants, like how this weight are same for the like 2 operation, like L minus 1, L minus 1, and L minus 2?
Yeah, very good. So what you can do is to so actually your CFT Hamiltonian is given by L0 plus L0 bar. Okay, so you can find the energy of the state by acting by this Hamiltonian. So for this level 2 states, so essentially this L0 is going to play a role because I'm just writing the holomorphic or the left moving part only. So what you can do is to look at L0, L minus 1, HP. Okay, and the eigenvalue of this is going to be HP plus 2, L minus 1, HP. And this is, and if you do it for this state as well, once again, you get the same eigenvalue. Okay. Does that answer your question? Yes, there is one more question.
Yes, I was asking how you are setting the ordering for this partition. Like for 3, you will have 2, 1, and 1, 2. Are they related?
Yeah, the ordering does not matter.
Okay.
Yeah. So in the, so for example, you can calculate the partition function. So these are degenerate states. So only the amount of degeneracy is going to appear in the partition function. So the ordering does not matter.
You need linear. answer, just a quick comment. You need linear independency. So L2, L minus 2, L minus 1 can be written in terms of L minus 1, L minus 2. So they're basically the same thing.
I have a kind of a psycho question. So can I go ahead?
Yes.
Yeah. So like so I mean, so when we study like the hydrogen atom, right? There's like we have these degeneracies of states and stuff. But then what I can do is I can take like a hydrogen atom and then put it in an electric field, and then I have like a stark splitting. Or if I put it in a magnetic field, I get a sort of Zeeman splitting of the degeneracy, right? So I was wondering if there is something that you can do to a CFT, a sort of violent thing that you can do to a CFT that kind of lifts the degeneracy of states that are the same.
Yeah, I mean, yeah, that's a good question. I mean, yeah, sorry, let this ambulance go. I mean, then. Yeah, so that's a good question. I don't know what the answer is, but one considers deformations of CFTs. I mean, you can consider some deformations of CFTs, which and engineer it in some appropriate way, which is going to do this for you. But I don't know what exactly one has to do.
What if, like, you know, you have charges or other symmetries in your system? Won't that break the degeneracy?
Yeah. So if you have additional charges, then there can be more descendants. For example, it's not just the Virasoro algebra, but there will be something more. Okay, and in that case, there will be more descendants. Say, for example, if I call additional generators as W, I can have something like W minus 5, L minus 1, HP. Okay, but there will be additional quantum numbers. Okay, there will be some additional quantum numbers corresponding to those additional symmetries.
But
now you can see whether these additional quantum numbers are different or not. Well, okay, so Madhu, probably to address your question, actually you can look at correlation functions of some observables in these descendant states, and those can actually be different for different descendant states. Yeah. For instance, you can look at the 2-point function. Yeah, this is something which is good. So you can look at the 2-point function of the stress tensor in this state and in this state. Okay, and that's going to, the answer to this is actually going to be different. Yeah,
I see. So basically this is saying that, you know, the spectrum, you know, the Hamiltonian cannot distinguish between these states.
Yeah, the
but
Hamiltonian, cannot distinguish because these have got the same energy. Yeah,
right.
Whereas if you look at like some other probes, yeah, this will give a different answer. Yeah.
I see.
But this introducing a chemical potential, isn't it like same like as putting the hydrogen atom in some magnetic effect? You have some more quantum numbers appearing, right?
Yeah, that is similar. Yes. So you can, so in your partition function, you can look at a slightly more general ensemble in which you turn on a chemical potential for this additional current, additional charge.
The L0 charge will depend on the W's.
No, L0 charge does not depend on W. So since the Virasoro algebra closes amongst itself, it does not depend on this additional charges. Yeah, it always depends on each. Yeah.
Okay, thanks.
Okay, so any other questions or comments? All right, so I have 15 minutes left. Let's see. Okay, so one can actually find what the contribution to the partition function from one single module or one single conformal family, which is the primary and its descendants. And there is this nice counting function which you can write, which is given by this infinite product. You can do a small Q expansion of this. And this is the generating function. So there is one state at level 1, 2 states at level 2, and like so on. So it counts the degeneracies at each order. Okay, so that's kind of a useful thing. So at each level, the number of descendants of the degeneracies is given by the integer partitions. And for large descendant levels, for large M, the growth is actually given by the Hardy-Ramanujan formula, which counts the interior partitions. Okay, so so in CFTs, since we have a lot of symmetries, we can find a number of observables by utilizing these symmetries. So we saw that the 2-point function of the stress tensor is fixed in this way. So it's a universal, but the central charge is something which is theory dependent. Similarly, the 2-point correlation function of primary operators also has the scaling law, which is this. So this delta depends on the specific details of the primary operator, which is again theory dependent. And you can also fix what the 3-point function of 3 primary operators, what it is going to be, and it takes this form. Okay? So the position dependence is completely fixed by conformal symmetries, but there is an overall proportionality constant that depends on these 3 operators. And this is nothing but the OP coefficient. Okay, so if you have 2 operators, bring them close to each other, you can write it as a linear combination of other operators, and the coefficients that enter this linear combination is the OP coefficient, and that's the number that appears over here. Okay, so these formulas are universal up to these numbers. Okay, these actually form the data of a CFT. Okay, so these are the specific details of a given CFT. So how does one find higher point correlation functions? So those are not completely fixed by conformal symmetry. Those those are theory dependent, and they depend on these numbers. So how does one find those? So that brings me to this CFT engine. So the higher point functions in CFTs, they can be evaluated by using the structures which are fixed by symmetries. So you have the conformal field theory, and it has got some structure built into it. Namely, these are conformal blocks. And you can plug in the data that corresponds, which consists of your central charge, operator dimensions, and the OP coefficients. And you can use this machinery of conformal blocks in order to calculate observables of interest, like higher point correlation functions. So like the 4-point function, which can have a lot of uses, like calculating entanglement entropies, OTOCs, and so on. You can use these symmetries and combine it with the information about a given CFT in order to find these observables. So what is this? What is this conformal block? So we need to understand what is the machinery which is built into a particular CFT. So consider the 4-point function of 4 primary operators on a plane. So we can take this and we can simply insert a complete set of states, which is nothing but the resolution of the identity. And so this is a sum over all states. So it's a sum over primaries as well as its descendants. But we can reorganize this sum and write it as a sum over primaries alone. So it's we can write this as a sum over primaries alone. And what happens is that you have this factor, which is the combination of these OP coefficients corresponding to these 4 operators. So P denotes the operator that you sum over. Okay, so this is the operator in the intermediate channel. So these are the external operators, and you sum over all possible exchanges. Okay, so that's this P. And all the position dependence sits within this conformal block. Okay, which is this. Okay, so these are just numbers, and this conformal block is an object which is fixed by conformal symmetries, and all the position dependence sits within the conformal block. Now, a useful analogy which I like is that of the partition function. So in case of the partition function, we can always write it, I mean, for any system, we can write it as a sum over Boltzmann factors. So the partition function is a function of temperature. So the theory dependent information enters via the degeneracies, while all the beta dependence or the temperature dependence sits within the Boltzmann factor, and it is universal. Okay. So the Boltzmann factor is a building block for the partition function. And analogously, in a conformal field theory for correlation functions of this kind, all the position dependence sits within this conformal block. So this is the analog of the Boltzmann factor, whereas the theory dependent information enters via these OP coefficients, which are this. Okay, so so this blocks, as I said, it's fully constrained by conformal symmetries, Virasoro symmetries in 2 dimensions. However, this is one place in physics where having a lot of symmetries makes your problem difficult, not easier. So owing to this infinite dimensional symmetry coming from these Virasoro generators, there are an infinite number of them. So given a primary, there are an infinite number of descendants. So these blocks are not known in closed form. So although they are fixed perturbatively, they're not known in closed form. However, they have been explored in various regimes of parameter space. So these blocks are functions of the operator locations of the external operator conformal dimensions, and the intermediate exchanges, the conformal dimension of the primary operator corresponding to that. So one can look at, and it also depends on the central charge. So one can look at the block in various regimes of these parameters, and there are closed forms available in some special regimes. Okay, but it's not known in full generality for throughout the parameter space. Okay, so these blocks will be useful, I think, for the lectures on quantum chaos, which will make an appearance over there. Okay, so now let me comment a bit on rational versus irrational CFTs. There was a question about this earlier. So the symmetry algebra of a CFT can be generated by n number of conserved currents. So usually if you have the Virasoro algebra, if you have that as your symmetry algebra, there is just one conserved current, which is that of the stress tensor. But you can have more general conformal field theories in which there can be more currents, like additional conserved currents as well. So for the case of the single free boson, it is the current J. So this is more fundamental than the stress tensor, because the stress tensor is given by the quadratic combination of these J's. So there's one single conserved current in the free boson theory. So rational CFTs are defined as CFTs in which the central charge is less than the number of conserved currents. Okay, so you might have heard of minimal models. So these have central charge less than 1, and 1 is 1 corresponding to the stress tensor. That's the only thing that is conserved. So C less than 1 corresponds to a rational CFT. Whereas irrational CFTs are CFTs where the central charge is more than the number of conserved currents. Okay. So as you can see, the central charge is a measure of the number of degrees of freedom of your system. And over here on the right-hand side of these inequalities, you have the number of conserved quantities. So if the number of degrees of freedom are lesser than the number of conserved quantities, your system is integrable. Okay. And what that implies is that rational CFTs are integrable or super integrable. I mean, if the number of conserved currents is more than the number of degrees of freedom, it's super integrable. If it's equal to the number of degrees of freedom, it's integrable. But if the number of degrees of freedom are larger, if the central charge is larger than the number of conserved currents, it's not integrable anymore by using our intuition from classical dynamics. So there is a possibility of chaos in irrational CFTs, but that's not possible in rational CFTs. Okay. Any questions at this stage?
I have a question. Like, so
yeah,
intuitively that statement is clear, but like once you start talking about like central charges which are not integral and so on, it's not really mapping to the degrees of freedom, right? It's a bit more abstract.
Yeah, it's a bit more abstract than that. Yeah.
So like, so in a more abstract way, how do you justify the statement about integrability and so on when you have a rational?
So yeah, I cannot. I mean, I cannot justify. I mean, you can calculate, like you can calculate various probes. For example, you can calculate OTOCs in a rational theory and in an irrational theory and see how the behavior is actually different. Okay. So in an irrational CFT, there is an exponential behavior at late times, whereas in a rational CFT, it will go to some constant, like the OTOC will go to some constant. Yes, to be more precise, I mean, you have to calculate some probes, which are of interest for that specific context. Yeah, but yeah. Yes, there is.
Do the holographic CFTs also fall in these categories, these rational or irrational?
Yeah, no, so now it's hard to like give one single sentence answer to this. So usually you expect that CFTs with which this CFT, which is going to be dual to Einstein gravity in ADS3, that's going to be an irrational CFT. That's the expectation. We still don't know what the CFT is. We don't even know what is the space of CFTs, irrational CFTs for C greater than 1. It's something which we still don't understand properly. Now, in stringy constructions, you can consider the symmetric orbifold. I mean, the symmetric orbifold is, say, for example, the symmetric orbifold of T4. You start with 4 free bosons and 4 free fermions. So that would again fall under this category. Okay. So, yeah. So in various different examples, I mean, you have different things. I mean, there are some higher spin CFT dualities in which the CFTs are built out of coset constructions, and in that case, those are rational CFTs. But yeah.
Okay, thanks.
Okay. So how much time do I have left?
Could you say a bit more about that previous comment? Because once you have like central charge is roughly like n, right? And then the currents are also, there are so many conserved currents also. So how do you make this comparison?
Sorry, I didn't understand the question.
No, I'm saying the holographic theories means central charge is like n, right? It's a large number.
Yes.
And I guess conserved currents are also, there are so many conserved currents with various strings of operators. So how do you make this comparison when once you go to some large kind of limit? How is this numbers compared?
Yeah, so usually I mean, in some cases, like n goes to infinity, and then C also goes to infinity. I mean, so in that case, I mean, yeah, I mean, you would still think that it is in the borderline rational regime. Yeah. If the, I mean, you can look at the ratio. I mean, if it goes to 1, I mean, then it's still in the borderline, this regime. I mean, for the symmetric orbifold, I mean, that is what happens, for instance.
Thanks.
So how much time do I have left? Sorry, I didn't.
Yeah, I mean, we can go for 10 minutes more, but I mean, we won't have time. I mean, we won't have any time for questions. Like, I mean, we have a strict cutoff at 4:15.
Oh, yes. Okay. So, okay. So let me like go through this section in brief, and then we can. Yeah. Okay. So we can consider CFTs on the torus. So these are systems at finite temperature and at finite spatial direction. So you have 2 periodic directions, and therefore you're on the torus. So you can cut open the torus, you get a finite cylinder, and you can cut open the cylinder and get this rectangle. Again, you can identify the opposite edges and get back the torus. Now you can do things to your torus. So this is your unwrapped torus, which is the rectangle. You can take this upper edge and shift it by 1 unit, which is L, towards the right. So this is like doing a shear. Okay. And the aspect ratio, this is something which is called the modular parameter. It's the ratio of lengths of this direction and this direction. This changes as tau goes to tau plus 1 if you do this. Okay. Note that if you still identify the opposite edges, you get back the same torus. Now, what you can also do is to exchange the cycles of the torus, and that corresponds to this sort of a rotation, which is this. So this is like swapping the cycles. And under this action, your modular parameter tau, it goes to 1 over tau. This is something which is called the S modular transformation. Again, if you identify the opposite edges, you get back the same torus. So these three surfaces represent the same surface. So if you place your theory, your two-dimensional conformal field theory on any of these surfaces, it should yield the same partition function. So that is this statement, okay? Now this is a purely geometrical constraint which comes from this, and this is a constraint on the spectrum of your theory. The partition function should obey this condition. And more formally, you can write it as this modular invariance. You can think of the torus as this parallelogram with opposite edges identified. You have got two vectors, basis vectors for this parallelogram. And you can, these basis vectors, you can do linear transformations to this. And under this specific linear transformations, you still get back the same torus, so which is this transformation. And as I said, the partition function remains invariant under this transformation. Okay, so now let's consider the S modular transformation in detail. So that's tau going to -1 over tau, which is nothing but exchanging the cycles of the torus. So tau over here is defined as this, whereas over here it's defined by the inverse ratio, which is this. Now this actually relates the low and high temperature expansions in a conformal field theory. So if you look at a conformal field theory quantity, the low temperature expansion of that is going to be in this parameter Q. So it is easily minus beta by L. So at low temperatures, beta is large. So this is a small quantity. Whereas at high temperatures, the relevant parameter for expansion is this. So it is e to the minus L by beta. So at high temperatures, beta is close to 0. And this Q bar, which has a 1 over beta in its exponent, if this thing is small. And what this S modular transformation does for you is to relate this low and high temperature expansions. So the partition function is given by the stress over this Boltzmann factor, which is this. And you can write this in terms of this zero mode of the Virasoro generators. It's given by this. Now, you can also write this partition function. It's a sum over states. You can also write this as an integral. This is an integral over the density of states. This is this. And rho of E is nothing but this. So if you just plug this thing over here, you get this back. Now, what you can do is to use the S modular transformation and just usual Laplace transforms in order to get a universal information about the spectrum of the CFT. So let's look at low temperatures first. So at low temperatures, the dominant contribution is going to come from the ground state of the theory. That is this. Okay, so that's the ground state. And now you can heat it up. You can go from low temperatures to high temperatures by doing a S modular transformation. And doing an S modular transformation of this gives you this. So that's the high temperature version. Okay, so the high temperature partition function. Now, we saw that the partition function can be written as an integral. It's an integral over the density of states. It's this. So the form of this integral is that of a Laplace transform. Okay. So one can extract out rho of E by an inverse Laplace transform. Okay, so we look at this and we try to extract what this density of states is by doing an inverse Laplace transform. So this is what you can do. So it's given by the inverse Laplace transform. You can evaluate this by using the saddle point method. So at high temperatures, the dominant saddle unsurprisingly comes from high energies. So beta star goes to 0 as E is large. And thereby you can evaluate the inverse Laplace integral this form. Okay. So we see that the density of states at high energies grows exponentially, and there is a square root of E in the exponent. Okay. So this is a celebrated result, which is called the Cardi formula. And it's a very strong and universal statement on the spectrum of any two-dimensional conformal field. Okay, and this is one of my last slides. So, so we know that some features of holography or ADS-CFT are universal in the large N limit. This consists of correlators, thermodynamics of black holes, entanglement. And the Bekenstein, you can find the Bekenstein-Hawking entropy of the BTZ black hole, which is a black hole in 3 dimensions and asymptotically anti-de Sitter space. And that actually has got this form. And if you take e to the s of this result, it precisely matches with this part. Yeah. Okay, so yeah, so that's more or less all I have to say. So here are some references which you can look up for further reading. I've also made a little exercise, so just to get some practice on conformal transformations. So we saw that conformal transformations are useful in order to calculate various correlators. This is an example which will allow us to calculate the finite temperature correlator. So the 2-point function of currents is actually given by this formula, as we saw earlier, and it transforms under conformal transformations in this way. Now you can directly use this conformal transformation in order to arrive at the finite temperature correlator. And that's going to take this form. Okay. Now, how do we know that this is the correct result? So what you can do is to rederive this finite temperature result by doing a sum over images calculation. So when you're at finite temperature, your time direction is periodic. So you essentially need to sum over images of the answer on the plane. So that's what you do over here. And if you do the sum, yeah, you will recover this result again. And similarly for the stress tensor, you can again derive the finite temperature correlator by using conformal transformations, and it takes this form, which is essentially the square of this result. And so these three parts might already be known to you, but the trickiest part of this question is to recover this result for the 2-point function of the stress tensor by doing a sum over images. And if you naively sum over images of the plane of the correlator on the plane, you are not going to recover this result. So the question is like, what is going wrong and what are we missing and how can one fix this? Yeah, so so the first 3 parts are not important. I mean, just feel free to read through it, but you can try this part D, and maybe you can post your answers on Slack and we can discuss it there. Okay, so that's all I have to say. Thanks for your attention.
We might have time for one quick question. Yeah, MSc. Oh, sorry. Yes. Okay. There's no question. It seems. Okay. Oh no.
Yes.
Yes. So in phase transition, so these primary descendant operators, what will be that physical analog there? Like we will compute only correlator.
Right, right. So actually one can look at the Ising model, for example. So the Ising model has got 3 primary operators, which is identity, and there is an operator corresponding to the energy, and there is another operator called sigma. So, so this energy is operator corresponds to changes in temperature. Actually, it is the conjugate operator corresponding to temperature. Whereas there is another primary called sigma that is conjugate to the strength of the magnetic field. Yeah. So these. Yeah.
What is the role of descendant operators there?
What is the role of descendant operators? Yeah, I don't know. I mean, what is directly the role?
So in partition function, you wrote some dn.
Yeah.
That is number of descendant operators.
Right. Right. I mean, if you want to calculate something like the free energy at that critical point, I mean, that's given by the partition function, and then the descendants are going to contribute. But what is the precise identification of descendants to the lattice system? I don't know. Yeah, maybe if someone knows, I mean, please feel free to speak up. I mean, yeah, I don't know that.
So like, I mean, we can thank Shouvik for his introductory lecture, and we can take a quick 5-minute break, after which from 4:30 I mean, we will be having the second session on alternate carrier for theorists. Please join. Like last day was quite good. Like.
Madhu.
Yep. What's up?
Probably this was too simple.